So this is going to be a good start for Terry. There goes the lightest of them. And Colin, he's got a good chance. He came through his heat very strongly.
I don't think we can judge how good Terry is comparing him to Brian in the fingers. Brian could well win this, in fact, very likely to win this event. So if Hollands can hang close, then it'll be good points in this event.
Well, Terry Hollands, he's playing catch-up at the moment. Brian Shaw has gone off like the proverbial rocket. And here goes the last of the Fingal's fingers. That is huge.
Hello everyone and welcome to Strongman Math Class. Let's talk about Fingal's fingers. First of all, a quick history lesson because I didn't know where the name Fingal's fingers came from, so I looked it up, and it turns out Fingal is the name of a mythological hero from Irish and Scottish folklore. There's a bunch of legends about him, including one about how he built the Giant's Causeway in Northern Ireland so he wouldn't have to get his feet wet. Fingal was a giant, according to the legends, so now the strongest men in the world test their strength by lifting his fingers, and that's where the name Fingal's fingers came from. That's all the history we have time for, so let's do some math. The common wisdom about Fingal's fingers among strongmen is that it's a tall man's event, and it seems to make intuitive sense that taller athletes should have an advantage, but I want to try to quantify that advantage, so that's what we're going to do here. Here's the setup of the event, and just in case anyone doesn't know, Fingal's finger is pretty much just a big metal pole that's hinged and anchored to the ground at one end, and the object is to pick it up by the other end and flip it over the hinge. Now, to quantify any advantage that taller athletes have, we're eventually going to want to compare the amount of force some athletes of varying heights need to generate at a certain point. But I think the best way to get started is going to be to look at torque rather than force. Torque is a word you've probably heard before, but you may not be familiar with precisely how it's defined in physics. You can think of torque as a rotational force, and it's defined as force applied times distance from the point of rotation. The unit for that in freedom units is going to be foot-pounds. So just to illustrate that with a quick example, if we applied a force of 100 pounds to this finger at a distance of 10 feet from the hinge, the torque applied would be 100 times 10 or 1,000 foot-pounds. So the reason we're starting with torque rather than force is that this event involves the athlete walking his hands up the finger as he lifts it, which means the point at which he's applying force is going to be constantly changing, and that in turn will change the amount of force he has to apply. Torque, on the other hand, only depends on the angle of the finger, as we'll see in a minute. So once we know the necessary torque, we'll be able to calculate the force required for any given point along the finger's length. So let's calculate the torque necessary to lift this finger. First, let's start with a few assumptions. First assumption is that the finger is uniformly weighted. I'm not actually sure if Fingal's fingers in contests are typically like this, but we're going to assume it for the sake of simplicity. All it really means is that the finger's center of gravity is going to be located directly in the center, at a distance from the hinge of half the finger's total length. I guess it's possible that promoters sometimes add weight in the end that's being lifted to adjust the weight for different classes. I don't know, I've never done a contest with this event in it before, but if that were the case, then adding weight to the end would just move the center of gravity farther from the hinge, but we're not going to worry about that here. Second assumption is that the finger is 12 feet long and weighs 600 pounds. These numbers are pretty arbitrary just for the sake of having some numbers to work with, but just for a point of reference, according to my research, this is a pretty good size finger for a World's Strongest Man event. If you look at the World's Strongest Man website, you'll find that the last time this event was included in Worlds in 2014, the second or third heaviest finger in the series was about this size, so this would be a pretty heavy one for us non-professionals. Third assumption, the hinge is 4 inches off the ground. We could just ignore this, put the hinge at ground level, and probably still come up with some pretty accurate results, but it's not that hard to incorporate, and it should make the results slightly more accurate. So working off of those assumptions, let's calculate the torque required as a function of the finger's angle. And to figure out how much torque is needed to hold this finger stationary at a certain angle, this torque, T, applied in the counterclockwise direction by the athlete must equal the torque created by the weight of the finger itself applied in the clockwise direction. To find the torque created by the finger's weight, we need to take the component of the finger's weight acting in a direction perpendicular to the finger and multiply it by the distance from the hinge at which it acts. That was kind of densely worded, so I'll explain. The total weight can be thought of as acting through the finger's center of gravity, which is directly in the center of the finger because we're assuming a uniform weight distribution, as we said before. So the distance part is half the length of the finger. Since torque is force times distance, we need to multiply that distance by a force, which is related to the weight of the finger, but not the same. What we want is the component of the finger's weight that acts in a direction perpendicular to the finger, and that force times this distance will give us the torque induced by the finger's weight. That force turns out to be the weight times the cosine of this angle, theta, and for geometry reasons, this angle theta turns out to be exactly the same as this angle theta. To illustrate that, picture the finger in a completely horizontal position. The angle between these two lines is now 0 degrees, and the angle of the finger relative to the horizontal is also 0 degrees. A similar thing happens if we put the finger in a vertical position. The weight still points directly downward, so the angle between these two lines is now 90 degrees, and the angle of the finger relative to the horizontal is also 90 degrees. So the bottom line of all that is that the torque the athlete needs to generate is equal to half the length of the finger, L over 2, times the weight of the finger, W, times the cosine of the finger's angle relative to the horizontal, theta. We'll just rearrange that slightly to make it look prettier, and we get this equation. Now we'll plug in the length and weight we talked about earlier, 12 feet and 600 pounds, and get some data to look at. Here's a graph of torque required as it relates to the finger's angle from 0 to 90 degrees. First thing to notice is here at 90 degrees, which would be a perfectly vertical position where we can see the torque required is 0 foot-pounds. That makes sense because you can imagine that if you could somehow perfectly balance the finger upright on its hinge, it wouldn't take any force at all to hold it there because the weight is acting directly downward through the hinge itself. The other point I want to take a look at is 0 degrees, or the horizontal position where the finger starts. And we can see that here the torque required is at its maximum of 3,600 foot-pounds. And this being the maximum torque required also makes sense because in this position the weight vector is pointing exactly perpendicular to the finger. Let's also look at something kind of interesting about this. So if you think about what an athlete actually does when he flips one of these things, the first movement is more or less something like a clean and press of this end of the finger. So if we take a snapshot of this at the exact moment the athlete first applies force, we know that in this horizontal position he has to apply at least 3,600 foot-pounds of torque. But for all intents and purposes, that force is applied at the very end of the finger, or 12 feet from the hinge, so we can calculate the amount of force needed, which is 3,600 divided by 12, or 300 pounds. Notice that 300 pounds is half the total weight of the finger. And that'll sound familiar if you watched the last video about tire flipping, where we used a different method to figure out that the initial force it takes to pick up one side of a tire from the ground is half the total weight of the tire. And it turns out that this applies to anything like this, any movement where you're flipping a uniformly weighted object. You'll also remember from the last video that it turned out you actually have to apply more force than that when flipping a tire, but that was just because of body mechanics not allowing a human being to apply a force in a purely vertical direction. But on the Fingal's finger, that's not the case, because here we can actually apply a more or less purely vertical force when we first pick up the end of the finger off the ground. So everyone has to apply the same amount of force to initially get the finger off the ground. But we're interested in how height affects this event, and height will come into play in the next part of the movement where the athlete has the end of the finger locked out over his head. Now at this point I'm going to stop talking about height and start talking about reach instead, because that term will be a little more precise with how I'm defining it. It's not only the athlete's height that matters, but also the length of his arms. So I'm going to define reach as the distance from the ground to the center of the athlete's palms with arms extended overhead. That's palms and not fingertips, because no one uses their fingertips to lift a Fingal's finger, and what we care about is the point of contact with the implement, which is the palm. And theoretically, you could have a 6-foot-tall guy with really long arms and a 6'4" guy with really short arms who have the same reach, but this reach variable will take all of that into account, height and arm length together, and we'll be able to represent it with just one number. Now, just as a point of reference, I'm about 5'11", and I measured my reach floor to palms at 6'8", so not quite a foot more than my height. It might be different for you depending on the length of your arms. Now let's picture the finger in this position where the athlete has it locked out overhead, but hasn't yet started walking towards the hinge. Something you can probably guess just from looking at this picture is that as the athlete's reach increases, the angle of the finger in this position is also going to increase. And as we know from the last graph, that means torque required is going to decrease. So without even doing any more math, we can already tell that the greater the athlete's reach, the less torque they have to apply to hold the finger in this position. And since everyone is holding the finger at the same point, which is again 12 feet from the hinge for all intents and purposes, less torque required directly translates to less force required. But let's do some math and figure out exactly how much of a difference this makes. We want to know this angle theta as a function of the athlete's reach, and from that we'll be able to calculate torque required and force required. And we can find this angle with just a little trigonometry. The length of the finger, L, times the sine of theta equals the vertical distance from the hinge to the athlete's palms, which is the athlete's reach, R, minus the height of the hinge, H. So we get this equation, which we'll just use algebra to solve for theta and get this equation. L and H are both values we know, so now we can plug in some values for R and find the angle. And that's what I've done here with this graph. I've used some reach values from 6 feet to 8 feet, which I think should be a plenty big enough range to cover most people. A guy with a 6-foot reach would be pretty damn short, and if you think of a guy like Brian Shaw or Thor at a height of 6'8" or 6'9", I can imagine those guys would probably have way longer arms than a guy like me, so putting their reach at about a foot plus 3 to 4 inches greater than their height is probably decently accurate. I can't say for sure since I don't have their arm measurements, but 8 feet should be close enough on the high end of our range. So as you can see here, using this range of reach values, we can get anywhere from about a 28-degree finger angle on the low end to almost a 40-degree angle on the high end. So that's a pretty significant difference if we're talking about a reach difference of 2 feet, but obviously most people actually competing against each other aren't going to have that much of a difference between their reaches. So with these numbers on the left here, I'm recording a finger angle for every quarter of a foot, or every 3 inches. So we can see that for every 3-inch increase in reach, we're seeing about 1.5 degrees of angle increase, generally speaking. And I would venture a guess that for most competitions you'll ever go to, within any given division, most athletes will probably have reaches within about 3 to 6 inches of each other, unless you happen to have a couple outliers like a random super tall guy or super short guy. But let's see how this translates to torque and force requirements. To do that, we're just going to take these theta values and plug them into this torque equation that we came up with before. We can also calculate force required from torque, and all we need for that is to just divide the torque by the distance from the hinge at which the force is applied. And in this case, everyone is applying force at the very end of the finger, so that distance is the length of the finger, L. So we're using this equation to calculate force required. So here's a graph of that. Same range of reach values on the x-axis from 6 feet to 8 feet, torque required over here on the left y-axis, and force required over here on the right y-axis. You can see that torque and force are the exact same curve, just on different scales, and that's because it's just a simple division by a constant to get force from torque. So with this setup, it turns out an athlete with a 6-foot reach has to hold up about 264 pounds, while an athlete with an 8-foot reach only has to hold up about 230 pounds. But again, almost no one is actually that far apart from other competitors in their own weight class at most competitions. So if we look again at the difference in force required for a 3-inch change in reach, we're seeing about a 4 to 5 pound decrease in force requirement per 3 inches of reach gained. So if you have a reach 3 inches taller than your competitor, you're probably holding up about 5 pounds less than him in this position at the most. So does reach make a difference in this event? Well, yes, but it turns out not a very big difference for most people, at least in this specific position, unless you're just freakishly taller than your competition. But this specific position isn't the only one we care about, obviously. The next thing the athlete is going to do after getting to this position is to walk his hands down the finger, pushing it further and further up until it passes through that vertical position and he can let it fall to the other side. Now, I'd like to see how the force the athlete has to produce changes as he walks his hands towards the hinge. And this is where we're about to see the value of calculating torque first rather than force, because while force changes with both finger angle and the athlete's position, torque changes only with finger angle. So we're going to first calculate torque, and then we'll be able to get force using that along with position. But we're also going to have to calculate some other stuff, so I'll take you through the whole process. What I've done is I've written a simulation in Python that will let us see how the force requirement changes as the athlete moves forward. So here's an outline of the process. First, we'll calculate the initial finger angle and athlete's distance from the hinge in that initial position with the arms extended overhead at the very end of the finger. The angle part of that is what we already did before, but we'll also need the athlete's horizontal distance from the hinge in this case, and you'll see why in a minute. Next, we'll use that finger angle to calculate the torque requirement, which we've also done before. Then we'll use that torque and distance to get the force requirement. And that gives us all the numbers we want to know about for that particular position. So next, we'll increment the athlete's position and reach by a small amount, which simulates the athlete moving slightly forward towards the hinge. Now, it's probably obvious why we're incrementing the distance, because the athlete is stepping forward. But you might ask why we're incrementing the reach, because the athlete's reach shouldn't change, right? Well, not exactly. If you watch people actually do this event, you'll see pretty quickly that their body position changes as they move forward. Specifically, they start to lean further and further forward as they move, and that means that effectively the athlete's reach is actually going to decrease as he moves forward. Now, this is another one of those details that we could probably just ignore and still get pretty accurate results, but it's not that hard to implement into the simulation, so we might as well just do it. As far as exactly how much the athlete's reach decreases, well, that's a little tougher to measure, so I'm just going to pick a fairly arbitrary number and say that the reach is going to decrease by 1 inch for every foot the athlete moves forward. So after we've incremented the position and reach, we just need to repeat the process using these new values, and then repeat until the finger gets to a vertical position. Now, what exactly goes into each step? Well, let's look at some equations. For step 1, to calculate finger angle, we're going to use this equation that we've seen before, and this is just the inverse sine of the ratio between the vertical side and hypotenuse of the triangle formed by the finger and the athlete. This r minus h, reach minus hinge height, is the vertical side, and s is the hypotenuse. Now, you might notice that when we saw this equation before, it was an L here on the bottom of this fraction, but now it's an S. That's because L is the length of the finger, which always stays constant, but the point where the athlete makes contact with the finger is constantly going to be changing. So I'm using S to represent the distance from the hinge to the athlete's hands. And for this first iteration through the process, S is going to be the same as L, but as we go forward, it's going to decrease. So then we want to calculate the athlete's horizontal distance from the hinge, because that's the value we're going to be incrementing at the end of every iteration. And if you remember your Pythagorean theorem from middle school, this equation is just that rearranged. For step 2, torque is something we've also calculated before using this equation. Then in step 3, we want to use that to calculate force, which is torque divided by S, which again is the distance along the finger from the hinge to the athlete's hands. And here again, when we saw this equation before, we were dividing by L, but now we're dividing by S because the athlete's hand position is constantly changing. Then we need to increment position and reach. This minus equals is just a symbol that means decrease this variable by this amount. So if D was 6, now it's going to be 5.9 after this step because we're decreasing it by 0.1. 0.1 is just a small enough step size that we'll end up being able to see plenty of detail in the data we end up with. And then, like I said before, we're decreasing R by 1/12 of that. And then we repeat the process. But this time through, we need an extra step because we don't yet know what S is after we've changed D and R, but we know it's not equal to L anymore. So before we repeat, we're going to calculate a new S value with this equation, which is just the Pythagorean theorem, again rearranged in a different way. So that's the simulation, and this will give us a couple different values that will be interesting to look at. So let's run the simulation and see what we can find. Alright, so here's a graph of some data from the simulation. Let's see what we can learn from it. This graph shows force required here on the y-axis as a function of finger angle on the x-axis, and we have separate curves for 9 different reach heights in 3-inch increments from 6 feet to 8 feet, which is the same range we were looking at before. Now you'll notice that the curves for the different reaches all start at different angles, and that's because we're starting from the position where the athlete has the finger initially locked out overhead, and we know that the greater reach an athlete has, the greater angle he's able to achieve in that position. So the guy with the 6-foot reach starts here at about 28 degrees, and the guy with the 8-foot reach starts at about 39 degrees. So for each of these curves, the force required initially increases as the athlete walks his hands down the finger and pushes it up, until we get to this maximum value at about 47 degrees. After that, the force requirement decreases until it finally goes down to 0 when the finger is at a 90-degree angle or perfectly vertical. So we can see that this maximum force value decreases as reach increases, and that makes sense based on what we've already seen. The greater your reach, the less force you have to generate at a given point. And here's a graph of that. The blue curve shows the maximum force required decreasing with increased reach, and the red curve shows that the point where the maximum force output occurs stays pretty much constant at right around 47 degrees, regardless of reach. The line is a little jagged because of computer rounding errors, but for all intents and purposes, it's a constant. So let's look at the actual numbers for maximum force output. Remember before, when we were looking at the initial locked out position at the end of the finger, that the force requirement only decreased by about 4 to 5 pounds for every 3-inch increase in reach. Well, it turns out that here at the point of maximum force output, there's actually a bigger difference. When reach increases from 6 feet to 6'3", maximum force requirement decreases by about 18 pounds. On the other hand, for a reach increase from 7'9" to 8 feet, also a 3-inch increase, maximum force decreases by about 10 pounds. So the difference here is more significant than it was in the initial locked out position, and it also turns out that for taller athletes, reach differences become less significant than for shorter athletes. So if my reach is 7'6" and yours is 7'3", that makes a slightly less significant difference than it would if we still had the same 3-inch difference, but my reach was 6'3" and yours was 6 feet. Here's a graph of some similar but slightly different information. Force required is still here on the y-axis, but now on the x-axis, instead of finger angle, we have horizontal distance from the hinge. So think of this like the hinge is over here on the left end of the axis at 0, and the athlete starts at this end and walks this way. So again, these curves start at different locations, and that's because the taller athletes will end up being slightly closer to the hinge in that overhead locked out position. So just like the last graph, we see that the force requirement increases up to a maximum as the athlete walks forward, then decreases down towards 0 when the athlete gets right up next to the hinge and the finger gets to the vertical position. Unlike the last graph, the point of maximum force output is not staying constant, but is actually moving farther away from the hinge as reach increases. So the 6-foot reach guy gets to his point of maximum force output at about 4.68 feet from the hinge, whereas the 8-foot reach guy is 6.73 feet away when he's generating maximum force. But as we know from the last graph, the finger angle will be at about 47 degrees in both cases. And this is why taller athletes have to generate less force. We know that torque only varies with finger angle, so both of these athletes are generating the same amount of torque when the finger is at 47 degrees. But the athlete with the greater reach is standing farther away from the hinge to achieve the same angle. If we look at the equation for force again, this d is the distance from the hinge at which the force is applied. We know torque stays the same for both athletes, but d is going to increase for the taller athlete because he's standing farther away from the hinge. When the denominator increases, this fraction gets smaller and therefore force decreases. So again, here's a graph of that distance information, and the red curve shows that as reach increases, the distance from the hinge at which maximum force output occurs also increases. Lastly, I want to say a quick word about these maximum force values. When I first ran these numbers, I was a little bit skeptical of this 242 number. Remember I said that the finger weight and length we're using is approximately the size of the second or third heaviest finger in the series at Worlds 2014. This 8-foot reach guy is pretty much a guy like Shaw or Thor, so what the math seems to be telling me here is that the maximum force Shaw or Thor has to produce at any point along this finger is only about 242 pounds, which seems super light for guys like that. Now I'm fairly confident that I didn't make any math mistakes while doing this, so the numbers say what they say. But I do want to point out one key assumption we made to start this problem, which is that the finger is uniformly weighted. I actually have no idea whether or not this assumption holds true at Worlds. It is possible that the fingers are more weighted towards the end, And if that were the case, the center of gravity would move farther from the hinge, which would increase the torque necessary to lift the finger, and in turn the force requirement would increase. So that's one possibility as to why my numbers here might be lighter than reality. Another possibility is that my assumption does hold true, but I just have no frame of reference for how big these numbers should be. 242 pounds sounds light for World's guys, but on the other hand, this isn't just a straight up overhead press. First of all, you're not pushing vertically, you're pushing at an angle, which makes this more awkward. Second of all, a lot of the time you're pushing with one hand, which in a way almost makes this more like a circus dumbbell press than a barbell or an axle. And holding up 242 pounds with one arm doesn't exactly sound so light anymore, even for World's guys. So maybe my assumptions are good and this number is accurate. I'd be interested to hear input from anyone who knows more about the typical setup of this event than I do. So to sum up, let's go over a few conclusions from what we've learned. First, reach does make a difference in how much force an athlete has to generate, but probably not a very significant difference in most cases. The biggest difference we saw for a reach difference of 3 inches was less than 20 pounds, and that was for fairly short athletes at the point where the difference would be most significant. So maybe that could make a difference for you, but I'd still say your best bet is to just be stronger than the other guy. Second, the finger angle at which maximum force output occurs stays constant regardless of reach. That angle could change depending on finger length and weight distribution, but doesn't depend on reach. Third, the distance from the hinge at which maximum force output occurs increases with reach. So the taller you are, the sooner you get over that hump and get to coast. And lastly, differences in reach become less significant as the athletes get taller. So that's all I have to say about Fingal's fingers for now. Please leave your feedback in the comments. Let me know if I made any mistakes or if I left out something important. And feel free to suggest topics for future Strongman math class videos. This topic was suggested by YouTube subscriber Paul, so thanks for the suggestion, Paul. Thanks for watching, and I'll see you next time. If you like this show, there are many ways you can support it. You can talk about it on your own blog or podcast, you can share it on social media with your friends, or you can leave a rating or review on iTunes, Stitcher, or wherever you happen to listen to it. If you're watching on YouTube, you can subscribe to the channel and hit the thumbs up button if you like this video. Thank you for your support, and we'll see you next time on Philosophication.